We have mapped the surface of Mars more precisely than the ocean floor. We have sent probes 20 billion kilometers into interstellar space. But what lies beneath your feet right now, just a few kilometers down, we barely know. Is the Earth hollow? No. But what it contains is far stranger than any conspiracy theory. A hidden ocean 3 times larger than all the surface oceans combined. Life forms that depend on neither sunlight nor oxygen, whose generation lasts 10,000 years. A solid core that has slowed its rotation and now turns slightly backward relative to the surface. And 2 gigantic masses at the core mantle boundary whose composition no one knows. Perhaps the remnants of the protoplanet that formed the Moon. All of that just a few kilometers beneath your feet. Tonight, we're going down. Let's begin by honestly measuring what we know and how little it is. The deepest borehole ever drilled in human history is the Kola Superdeep Borehole in Russia, on the Kola Peninsula north of the Arctic Circle. The Soviets began drilling in 1970 with the explicit ambition of reaching the Mohorovicic discontinuity, the boundary between Earth's crust and the mantle. The project lasted 24 years. It was stopped in 1994, not because the goal had been reached, but because the temperatures encountered were far higher than predicted, around 300 degrees Celsius at that depth, versus the 100 degrees expected. So the drilling tools became uncontrollable in rock that behaved plastically rather than rigidly. Final depth reached 12.262 kilometers. An absolute world record, still unbeaten. To put that number in perspective, the thickness of the continental crust varies between 30 and 70 kilometers, depending on the region. The oceanic crust, thinner, is between 5 and 10 kilometers. Earth's radius is 6,371 kilometers. The Kola borehole penetrated about 0.2% of Earth's radius. We went through less than 1/5 of the way to the MOHO, the crust mantle boundary, which we have never directly reached anywhere. But what we found in that borehole already surprised geologists. Water at depths where pressure and temperature should have eliminated it. Not surface liquid water that seeped down, but water chemically released by minerals under the effect of pressure. Rocks whose properties did not match the predictions of the models. And a seismic discontinuity that geophysicists had detected using seismic waves at about 7 kilometers deep, interpreted as the transition between rocks of different composition, which turned out to be simply the same rock in 2 different states under the effect of pressure and temperature, not a change in composition. This result illustrates the fundamental limit of our knowledge of Earth's interior. We never observe it directly. We infer it. The primary tool is seismology. When an earthquake occurs somewhere on Earth, it generates seismic waves that propagate through the planet's interior in all directions. These waves, compressional waves called P waves, and shear waves called S waves, behave differently depending on the nature of the material they pass through. P waves travel through solids and liquids. S waves travel only through solids. By measuring the arrival times of these waves at seismographs distributed across the globe, geophysicists reconstruct an image of Earth's interior, the way a doctor reconstructs an internal image with ultrasound, but with considerable shadow zones and limited resolution. That's how we know the outer core is liquid. S waves do not pass through it, and that the inner core is solid. That's how the layered structure has been mapped. Crust, upper mantle, transition zone, lower mantle, outer core, inner core. For about a decade, a new window has opened: geoneutrinos. The naturally radioactive elements in Earth's interior, uranium, thorium, potassium-40, decay while emitting neutrinos. These particles pass through the entire planet without interaction and can be detected by ultra-sensitive instruments like CAMLAND in Japan. By measuring the flux and energy of these geoneutrinos, researchers are beginning to map the distribution of radioactive elements within Earth's interior. Information entirely inaccessible to seismology. The official structure of the Earth is established in its broad outlines, but it contains significant blind spots. The exact composition of the inner core is debated. Solid iron and nickel, yes, but with fractions of sulfur, oxygen, silicon, hydrogen, whose exact proportions are the subject of competing models. And two large-scale anomalies persist. Masses detected seismically at the core mantle boundary, at about 2,900 kilometers depth, which differ significantly from the surrounding materials and whose composition remains unknown. They are called the Large Low Shear Velocity Provinces, or LLSVP. One is beneath Africa, the other beneath the Pacific. Each is the size of a continent. We will come back to them. In 2014, a team at the University of Alberta in Canada, led by Graham Pearson, published in Nature the results of the analysis of a diamond brought up from the Juína mine in Brazil. Diamonds formed deep in the mantle sometimes rise to the surface via kimberlite eruptions, special volcanic eruptions that tap the mantle at very high speed. By examining this diamond in detail, the researchers found an inclusion inside it, a tiny fragment of a mineral called ringwoodite. Ringwoodite is a form of olivine, a magnesium and iron silicate that naturally exists only under the pressure and temperature conditions of the mantle transition zone, between about 410 and 660 kilometers deep. It cannot form at the surface or survive there. This diamond was therefore a hermetic capsule brought up from the depths, trapping a fragment of its place of origin. What made this discovery extraordinary? The ringwoodite in this inclusion contained water. Not in liquid form, water incorporated into the crystal structure of the mineral itself, hydrogen and oxygen atoms bound into the silicate lattice, representing about 1 to 1.5% of the mineral's weight. The implication is immediate and enormous. If the ringwoodite of the transition zone contains water at this concentration throughout its volume, and if the transition zone is homogeneous in this property, then the amount of water stored in this single layer is equivalent to about 3 times the volume of all Earth's surface oceans combined. 3 times. The planet's largest water reservoir would not be at the surface. It would be 400 to 660 kilometers deep, trapped in minerals at 1,400 degrees Celsius under a pressure of several 100,000 atmospheres. This water looks like nothing we know. It is not an underground ocean, not a giant aquifer, not liquid water in cavities. It is water in atoms, hydroxyl ions, OH, integrated into the crystalline bonds of minerals. Invisible to instruments that look for liquid water, inaccessible to any conceivable drilling, but real, confirmed, and on a scale that reorganizes our conception of the planetary water cycle. The classic water cycle, evaporation, precipitation, runoff, oceans, is the surface cycle. But tectonic plates carry water into the depths via subduction. When an oceanic plate sinks beneath a continental plate, the hydrated minerals of the oceanic crust transport water into the mantle. This water is gradually released as pressure and temperature increase. Some is trapped in mantle minerals, some comes back out via volcanic arcs. Volcanoes in subduction zones, like those of the Pacific, are partly fueled by this water recycled from the depths. It is a cycle of millions to tens of millions of years. Over the long term, it regulates the amount of water at Earth's surface, the stability of tectonic plates, and the dynamics of volcanoes. The 2014 study added an intermediate reservoir to this cycle, the transition zone as a buffer storage of water on geological timescales. Subsequent studies have detected signatures of water even deeper, in the lower mantle. In 2018, a study published in Science by a team at the University of California, San Diego, detected water inclusions in diamonds formed between 360 and 800 kilometers deep in the lower mantle. The distribution of water in Earth's mantle is more complex and more extensive than anything we had imagined. The implication for understanding planetary habitability is direct. If Earth stores water in its mantle and recycles it via tectonics, the long-term presence of water at the surface is partly controlled by this internal dynamics. Planets without active plate tectonics could sequester their water in the mantle and lose it from their surface. It is a relevant variable in evaluating the habitability of exoplanets. Surface water is not only a matter of orbit and temperature, it is also a matter of internal dynamics. In 1986, geologists from the University of Michigan explore a gold mine 3.2 kilometers deep in Precambrian rocks in South Africa, the Driefontein mine in the Witwatersrand region. They find water in fractures in the rock, and in that water, they find bacteria. Bacteria 3 kilometers deep in an environment without sunlight, without atmospheric oxygen, at temperatures of 50 to 60 degrees Celsius, under hundreds of bars of pressure. These bacteria derive their energy neither from photosynthesis nor from aerobic respiration. They feed on hydrogen, produced by the chemical reaction between water and the surrounding rocks, in a process called radiolysis. The natural radioactive decay of minerals splits water molecules and releases hydrogen. These bacteria live off the radioactive decays of uranium and thorium in the rocks. They have no metabolic link to Earth's surface. This discovery opened up an entire field of research, formalized in the 2000s and 2010s under the name Deep Biosphere. The Deep Carbon Observatory, an international research program involving about 1,200 scientists over 10 years from 2009 to 2019, produced the most complete inventory ever established of life in Earth's depths. Its conclusions, synthesized in a 2019 publication in American Mineralogist, are staggering. The total biomass of the deep biosphere is estimated at between 15 and 23 billion tons of carbon. By comparison, the total biomass of living beings on the surface, humans, animals, plants, fungi, bacteria, represents about 550 billion tons of carbon, 450 billion of which comes from plants alone. Subsurface microorganisms, therefore, represent several percent of the planet's total biomass. That is colossal. And until the early 1990s, we did not know it existed. This deep biosphere extends down to at least 5 kilometers deep in the continental crust, and presumably deeper in the oceanic crust. It includes bacteria, archaea, a domain of life distinct from bacteria, with radically different biochemical properties, and in the upper layers, fungi and multicellular organisms such as nematodes. The most extreme organisms in this biosphere defy our usual biological categories. A generation, the time between two cell divisions, can last from 1,000 to 10,000 years, depending on the species and the depth. These organisms are not slowly dying. They simply have a metabolism calibrated on geological timescales. They live at a pace that our biology cannot directly perceive. Bacteria kept dormant in very ancient sediments have been reactivated in the laboratory after millions of years of inactivity. A 2021 study published in Nature Communications by a team from the Japan Agency for Marine Earth Science and Technology revived microorganisms from Pacific Ocean marine sediments aged 101.5 million years, from the Middle Cretaceous, which began reproducing again after being cultured under laboratory conditions. These organisms were metabolically active at the time when dinosaurs dominated the Earth. They survived in very low-energy sediments for more than 100 million years. Methanogenic archaea, methane producers, have been identified at temperatures up to 120 degrees Celsius, close to the theoretical limit of life based on carbon chemistry and liquid water. Microorganisms breathe oxides of manganese, iron, uranium, metals present in rocks, the way some surface organisms breathe oxygen. The question of the lower limit of Earth's habitability is not settled. The ultimate constraint appears to be thermal. Beyond a certain temperature, biological molecules irreversibly denature. This limit is estimated between 120 and 150 degrees Celsius for currently known organisms. In Earth's crust, this temperature is reached at depths that vary depending on the local geothermal gradient, generally between 4 and 8 kilometers in the continental crust, and less in geothermally active areas. The implication for astrobiology is direct and has transformed the priorities of the search for extraterrestrial life. If life thrives without light, without oxygen, powered by radioactivity and rock chemistry, at high temperatures and extreme pressures, then the criteria for a planet's or moon's habitability are far broader than previously thought. Europa, Jupiter's moon, has a liquid ocean beneath its ice crust, kept liquid by Jupiter's gravitational tidal heating. If processes similar to radiolysis occur at the interface between that ocean and the rocks on the sea floor, microorganisms like those in Earth's subsurface could exist there. Enceladus, Saturn's moon, ejects plumes of water vapor rich in organic matter and silica from its south pole, a signature of hydrothermal activity in an internal ocean. And the subsurface of Mars, shielded from the surface's ionizing radiation by a few meters of rock, is now considered the most serious lead in the search for past or present life on the red planet. We have been looking for life in the stars for decades. It was under our feet from the beginning, and it is probably under Europa's ice too. At Earth's center, about 5,100 kilometers below the surface, begins the inner core, a solid sphere of iron and nickel with a radius of about 2,440 kilometers, roughly the size of the Moon. Its temperature is estimated at around 6,000 degrees Celsius, comparable to the surface of the Sun. It is kept solid not because it is cold, but because the pressure at that depth is so colossal, about 3.5 million atmospheres, that it forces iron to solidify even at that temperature. Around it, the outer core, 2,260 kilometers thick, consists of liquid iron and nickel in constant convection at about 4,000 to 5,000 degrees. This moving liquid metal generates, by dynamo action, Earth's magnetic field. This field protects the planet from the solar wind, the patok of charged particles emitted by the Sun, which, without it, would gradually erode the atmosphere. Mars lost its global magnetic field about 4 billion years ago. Its atmosphere has been progressively stripped away since then. Earth owes its atmosphere and oceans in part to the dynamo of its core. The inner core's rotation relative to the rest of Earth is an active and rapidly evolving field of research. The inner core, suspended within the liquid outer core and gravitationally coupled to the rocky mantle, can rotate at a slightly different speed than Earth's crust. In 2023, a study published in Nature Geoscience by a Peking University team led by Yi Yang and Xiaodong Song analyzed seismic waves passing through the inner core since 1964 and concluded that the inner core follows an oscillation cycle of about 70 years, super-rotating relative to the surface during one phase, then sub-rotating during another. In June 2024, a study published in Nature by John Vidale's team at the University of Southern California, analyzing 121 repeating earthquakes in the South Sandwich Islands between 1991 and 2023, as well as data from Soviet nuclear tests in the 1970s, confirmed and refined this picture. The inner core was in super-rotation, turning slightly faster than the surface, until around 2008. From 2008 through 2023, it shifted into sub-rotation, turning slightly slower than the surface, slowly returning along its previous path. In practice, this means the inner core is currently rotating slightly backward relative to the surface, in the sense that it does not advance fast enough to remain in the same relative position. The effect on daily life is imperceptible. Researchers speak of variations in the length of the day on the order of 1/1000th of a second. But the implications for our understanding of internal dynamics are significant. This oscillatory motion suggests complex coupling between the solid inner core, the liquid outer core, and the rocky mantle, interactions that likely influence the structure of Earth's magnetic field, even if the precise mechanisms are not yet well understood. A study published in December 2024 in Science News by the same Vidale team added a new complexity. The inner core also appears to change shape slightly over the course of this cycle, not just its rotation. Earth's magnetic field is not stationary. It varies in intensity and direction on timescales ranging from the year to the million years. Complete reversals, where the north and south magnetic poles swap, have occurred about 183 times over the last 83 million years, or on average about every 450,000 years. The last major reversal, called the Bruniss-Matuyama reversal, occurred about 780,000 years ago. So, statistically, we're overdue compared to the average. This delay doesn't mean a reversal is imminent. The distribution of intervals is variable enough that it doesn't constitute a prediction. But Earth's magnetic field has lost about 9 to 10% of its intensity since the first direct measurements were made in the 19th century. And the South Atlantic anomaly, a vast region above South America and the southern Atlantic, where the field is abnormally weak, about 30% below the global average, has expanded and deepened in recent decades. Satellites that pass through this zone record higher rates of electronic errors due to increased exposure to cosmic radiation in this region. If a reversal were to occur, it would not be instantaneous. Geological data indicate that a complete transition takes between 1,000 and 10,000 years, during which the field is weaker and more complex. The effects on modern technologies, navigation systems, power grids would be significant but not catastrophic. It would be an engineering challenge, not an extinction. The two LLSVPs, these gigantic masses at the core mantle boundary, are among the largest and least understood objects in geoscience. Each is roughly the size of the African continent in area and extends several hundred kilometers in height. Seismic waves travel through them more slowly than through surrounding materials, which indicates either a higher temperature, a different composition, or both. Their origin is unknown. One hypothesis proposed by several researchers, including Qian Yuan in recent work published in Geochemistry, Geophysics, Geosystems, is that they could be remnants of the protoplanet Theia, the impactor whose collision with the proto-Earth formed the Moon. If this hypothesis is correct, these two masses would be remains of the planet that gave birth to our natural satellite, preserved at the core mantle boundary for 4.5 billion years. They are geological objects older than any rock on Earth's surface. These masses are not inert. They influence mantle convection above them, in particular the formation of mantle plumes, columns of hot material rising from the depths toward the surface. The most active volcanic hotspots on the planet, Hawaii, Iceland, the Canary Islands, Yellowstone, are associated with mantle plumes whose deep sources are geographically correlated with the LLSVPs. An ocean 3 times larger than all surface oceans, invisible in the crystals of mantle minerals. Billions of tons of living organisms in total darkness, powered by radioactivity, some of which have a generation that lasts 10,000 years. A core that oscillates between superrotation and subrotation on a cycle of decades, whose mechanism we barely understand. And 2 continental-sized masses at the core mantle boundary, perhaps 4.5 billion years old, whose composition remains unknown. All of that just a few kilometers beneath your feet. We're obsessed with distant space, and that's legitimate. But the greatest terra incognita on our planet is the planet itself. We've drilled 0.2% of its radius. We read its interior through indirect seismic waves. We're only just beginning to detect its neutrinos. Earth's interior is, on the scale of human knowledge, as unexplored as the spaces between the stars. They say we know the sky better than the Earth. After tonight, you know why that's true, and why that should change.
Look at this diagram. It represents a view of the Earth cut in two, with its different internal layers. The first layer is the Earth's crust. This is the surface of the Earth, the part where we put our feet and walk every day. It's this layer that builds mountains and forms oceans. We speak of continental crust for the continents and oceanic crust for the oceans. As you'll see later, these 2 types of crust are very different in nature and composition. As you can see from this diagram, the crust represents only a very small part of the Earth. Its thickness varies from 5 kilometers or 3 miles under the oceans to 80 kilometers or 50 miles under the continents. More precisely, the Earth's crust represents around 1.5% of the solid Earth's volume and only 4.4% of the Earth's mass. Let's start by looking at the continental crust. The continental crust is thicker, older, and of lower density than the oceanic layer. Its thickness varies around 20 kilometers or 12 miles, but it can reach a thickness of 80 kilometers or 50 miles beneath major mountain ranges, such as the Andes. The continental crust is solid. It is essentially composed of granitic rock, with additional layers of sedimentary rock in some areas accumulated over millions of years. Volcanic rocks such as basalts can also be found on the surface. The continental crust is not confined to the continents. It extends under shallow waters near the coasts. These are known as continental shelves. This is why the continental crust covers around 45% of the Earth's surface, while the continents account for only 30%. The oceanic crust covers the remaining 55% of the Earth's surface. It is therefore more extensive, but much more discrete, since it is mainly submerged. It is denser and more homogeneous than continental crust. It consists mainly of basic rocks such as basalts and gabbros. These rocks are rich in magnesium, iron, and silica. They are denser than the granites that make up the continental crust. Although oceanic crust is denser, it is thinner than continental crust, with an average thickness of 5 kilometers or 3 miles. In short, oceanic crust forms the floor of the oceans. Let's take a closer look at the oceanic surface of our planet. Half of the ocean floor is made up of what are known as abyssal plains. These abyssal plains are located between 3,000 and 6,000 meters, or 10,000 and 20,000 feet deep. Then, near continents and islands, we find abyssal trenches, fissures where marine sediments accumulate. The oceanic crust also forms mountains with flat tops due to erosion. These are called goyots. Finally, chains of submarine volcanoes in the middle of the oceans form what are known as oceanic ridges. These ridges play a major role not only in the formation of the oceanic crust, but also in its renewal. Every day, the ocean floor moves, evolves, and changes. This phenomenon is imperceptible to the human eye, as each movement takes years. The process of creating oceanic crust resembles a cycle, or rather a recycling process. Imagine the action of a conveyor belt. Part of the crust is buried in the Earth's mantle by subduction, while new oceanic crust is formed by plate tectonics or submarine volcanism. The rate of formation of oceanic crust varies from one part of the globe to another. In the southwest Indian Ocean, for example, the rate of formation is estimated at 0.5 centimeters or 0.2 inches per year. This is very low, compared with a record of 16 centimeters or 6.3 inches per year held by the fastest oceanic ridge in the Pacific. Because oceanic crust is constantly being renewed, it is much younger than continental crust. Its age is estimated at just 200 million years, compared with 4.4 billion years for the oldest parts of the continental crust. Let's continue our journey to the center of the Earth. We're going to go under the Earth's crust even deeper. The layer beneath the continental crust, or Earth's crust, is called the Earth's mantle. We've just entered the heart of the Earth's most important layer. The mantle represents 84% of our planet's volume and 68% of its mass. It extends to a depth of 2,850 kilometers, or 1,770 miles, and drops to 2,900 kilometers, or 1,800 miles in places, at the boundary with the core. The mantle is separated from the crust by what is known as the Moho-Rivivik discontinuity, called the Moho. We are now about 100 kilometers or 62 miles deep inside the Earth. It's very hot here, over 1,000 degrees Celsius or 1,832 degrees Fahrenheit. So hot that the rocks of the Earth's crust are melting, creating a new layer that is part liquid and part solid. Part liquid, part solid is not the right term. In fact, the mantle is less solid than the Earth's crust, but it's not liquid either, contrary to what you might think when you watch lava flows emerge from the bowels of the Earth. More precisely, the Earth's mantle is solid, but it behaves like a viscous liquid. If we were in the mantle instead of on the Earth's crust, it would be like being in honey. Let's look at the problem from another angle. The viscous rocks that make up the mantle are solid, but capable of deforming over the very long term. But why, you may ask, is the mantle solid when it's made up of molten rock? Quite simply, because pressure conditions are such that they exceed temperature conditions. In other words, the mantle is under so much pressure that it maintains its solid state. Let's return to the viscous rocks of the Earth's mantle. This inner layer of our planet is made up mainly of silicate rocks, rich in iron and magnesium. Let's now take a look at the separation between the Earth's crust and mantle, which we call the MOHO discontinuity. We call it a discontinuity because researchers have observed a sudden acceleration of seismic waves as they cross this boundary. The MOHO is located at an average depth of 35 kilometers or 22 miles. It was discovered in 1909 by meteorologist and seismology pioneer Andrija Mohorovičić. He observed a sudden acceleration of seismic waves, explained by a change in the propagation medium. In other words, as they pass through the mantle, seismic waves accelerate because they propagate faster in the periodicites that make up the mantle. All projects to drill into the MOHO have been abandoned. The discontinuity is far too deep. Drilling down to the MOHO would require colossal technical efforts, and it would be extremely costly. The information we have gathered on this demarcation between the Earth's crust and mantle therefore comes mainly from the study of seismic waves. Below the MOHO discontinuity, the mantle is separated into two parts, the upper mantle and the lower mantle. As we descend towards the center of the Earth, it's the upper mantle that we observe first. Mainly made up of periodicites, the upper mantle lies between the MOHO and 670 kilometers, or 415 miles below the surface. If you followed this correctly, since the MOHO is around 35 kilometers or 22 miles deep, that makes the upper mantle almost 640 kilometers or 400 miles thick. In other words, the upper mantle represents only 20% of the mantle's total thickness. It is less viscous than the lower mantle and less hot, since the further down towards the center of the Earth, the hotter it gets. The temperature of the upper mantle therefore ranges from 440 degrees Celsius or 824 degrees Fahrenheit at the base of the oceanic crust to 1600 degrees Celsius or 2912 degrees Fahrenheit at the boundary with the lower mantle. It is the upper mantle that drives the movement of tectonic plates, which we'll be discussing later in this journey. In this inner layer of the Earth, we find minerals such as olivine, pyroxene, and spinel. The upper mantle has a special feature. It is separated into two parts by the low velocity zone. The LVZ lies between 100 and 200 kilometers, or 60 and 125 miles below the surface. Its depth varies according to the type of crust it underlies. Under oceanic crust, it lies between 30 and 90 kilometers, or 18 and 56 miles deep. Under continental crust, it's deeper, buried between 110 and 230 kilometers, or 68 and 143 miles, in the bowels of the Earth. It's so called because in this zone, seismic wave velocity is reduced. We'll talk more about the LVZ later, as it forms the boundary between the lithosphere and the asthenosphere, the secondary layers of our planet's inner structure. Going deeper, we enter a new layer, the lower mantle. This part is more extensive than the upper mantle, extending from 670 to 2,900 kilometers, or around 415 to 1,800 miles in depth. Composed mainly of perovskite and magnesio-wustite, the lower mantle is even hotter than the upper, as it lies deeper in the Earth's bowels. It can reach temperatures of up to 4,000 degrees Celsius or 7,200 degrees Fahrenheit at the boundary with the outer core. It's also denser than the upper mantle and becomes denser the deeper you go into the Earth's core. Around 2,700 kilometers or 1,700 miles deep, we find a zone known as the D zone, marked by a slowdown in wave propagation. This is the landing point for oceanic plates that have sunk after subduction. It is also the origin of hotspot plumes. The upper and lower mantle play an important role in the inner workings of our planet. The mantle is the seat of convection currents that transfer most of the thermal energy from the Earth's core to the surface. Although the precise characteristics of these currents are not yet known, we do know that they are at the origin of continental drift, which we'll talk about a little later. Let's continue our journey. We're going even deeper into the bowels of the Earth. We've now reached a depth of 2,900 kilometers or 1,800 miles underground. At this depth, scientists have observed another discontinuity, the Gutenberg discontinuity. It marks the boundary between the lower mantle and the center of the Earth, known as the core, as in a fruit. The core accounts for 15% of our planet's volume and nearly a third of its mass. It extends to a depth of 6,380 kilometers or 4,000 miles. It is composed mainly of iron and is divided into two parts or envelopes. These are the liquid outer core and the solid inner core. The liquid outer core consists mainly of molten iron, mainly but not exclusively. 80 to 85% of the liquid outer core is iron. The remainder is 5% nickel and 10% a light element that has yet to be precisely determined. It could be sulfur, oxygen, silicon, or carbon, or perhaps a mixture of several of these elements, or even all four. The liquid outer core lies between 2,900 and 5,100 kilometers, or between 1,800 and 3,200 miles deep. Its average temperature is 4,000 degrees Celsius, or 7,200 degrees Fahrenheit. The first envelope is a mass of molten metal, stirred by thermal convection. The movements of the outer core interact with the Earth's movements, notably its rotation, and in the longer term its precession, i.e., the slow change in direction of its axis of rotation. As iron is an electrical conductor, the iron-rich outer core will also allow the development of variable electrical currents. These currents give rise to magnetic fields, which in turn reinforce them. The result is the dynamo effect. It is thought that the liquid outer core is at the origin of our planet's magnetic field, but more on that later. The outer core is an envelope that surrounds the second part of the core, the solid inner core. The boundary between the two is marked by another discontinuity, the Lehman discontinuity. This boundary between liquid and solid lies at a depth of around 5,150 kilometers, or 3,200 miles. Prior to the discovery of this discontinuity, the Earth's core was thought to be entirely liquid. It was Danish seismologist Inge Lehmann who demonstrated the existence of a solid core inside the liquid core in 1936. This is why the boundary between the two bears her name. The solid core is composed of almost pure iron. It's also known as the seed. Imagine a solid ball made up of an alloy of 80% iron and 20% nickel. But why is the inner core solid? The answer is the same as for the viscous rocks of the upper mantle. The inner core is under much greater pressure than the liquid outer core. This pressure is 350 gigapascals, or 3.5 million times that of the atmosphere. This pressure maintains the iron core in a solid state, despite a scorching temperature that can exceed 6,500 degrees Celsius, or 11,700 degrees Fahrenheit. With a thickness of 1,216 kilometers, or 755 miles, the inner core is very dense. According to one of the most widely accepted hypotheses in the scientific community, the dense metals of which it is composed sank into the primitive Earth, eventually finding their way to the center and forming a solid ball. The inner core is the Earth's deepest layer. It is the heart of our planet. It is certain that we will never be able to drill to this depth. For the time being, therefore, the exact nature of the core remains open to debate. Some observations have concluded that it is in motion. It could be that the inner core is spinning inside the liquid outer core. But for the moment, once again, nothing is certain. We've arrived at the center of the Earth, but the journey isn't over yet. Remember that we spoke earlier about the lithosphere and the asthenosphere. These are two secondary layers of the Earth's interior. Most often we distinguish between the layers we've just explored, i.e. from the ground towards the center of the Earth, crust, mantle, and core. But other models incorporate the notions of lithosphere and asthenosphere. So let's take a moment to explore these two secondary layers, which are also important to the Earth's behavior. The lithosphere is the Earth's most superficial envelope. It is considered the Earth's rigid envelope. Approximately 100 kilometers or 62 miles thick, it comprises the Earth's crust, oceanic or continental, and the upper part of the upper mantle. It's important to point out that not all the upper mantle is included in the lithosphere. In fact, the lithosphere only includes the zone above the LVZ, which we mentioned earlier. The LVZ lies between 100 and 200 kilometers, or 62 and 125 miles, below the Earth's surface. It is below the LVZ that the upper mantle materials become ductile. To be ductile is to be able to stretch and deform without breaking. It is also under the LVZ that periodatites approach their melting point. As you can see, the LVZ marks a change in the behavior of upper mantle rocks. Above the LVZ, the rocks are solid, and below they are ductile. The Moho discontinuity is also found in the lithosphere. The lithosphere is subdivided into tectonic or lithospheric plates. Because continental and oceanic crust have different compositions, we sometimes distinguish between continental and oceanic lithospheres. The mantle also differs according to the type of crust it underlies. The subcontinental mantle, for example, is depleted in the chemical elements found in the suboceanic mantle, which is closer to the primitive mantle. The thickness of the lithosphere varies from one part of the globe to another. Under the continents, it is on average 100 kilometers or 60 miles thick, compared with just 70 kilometers or 43 miles under the oceans. The colder the mantle, the thicker the lithosphere. In regions with cold mantle, such as old continental crusts, it can reach a thickness of 200 kilometers or 125 miles. In warmer zones, such as ocean ridges, the lithosphere is only a few tens of kilometers thick. This is explained by a simple principle. As the oceanic lithosphere cools, it gradually thickens. It begins at the ridges, where it is very thin, and evolves to the continental margins where it is thicker. The older the lithosphere gets, the thicker it becomes, the greater its density, and the deeper it sinks into the mantle. The lithosphere plays a major role in plate tectonics. In the collective imagination, we tend to think of plate tectonics as follows. The continents are boats, floating on the ocean and drifting with the currents initiated by the movements of the Earth's mantle. The reality is more complex than that. It's the crust and lithospheric mantle that move above the asthenospheric mantle. These movements are driven by the laws governing the mechanical behavior of rocks, which themselves depend on pressure and temperature conditions. In fact, it's not the continents that move, but the rigid lithospheric plates. Separated from the lithosphere by the LVZ, the asthenosphere is less rigid than the lithosphere. Its behavior is more ductile. The asthenosphere is the lower part of the upper mantle. It lies between the LVZ and the lower mantle, between 100 and 670 kilometers, or 60 and 415 miles in depth. The partial melting of rocks in the asthenosphere creates low mechanical strength and low seismic velocity. It is the particular properties of the asthenosphere that allow lithospheric plates to move, and hence tectonic plates to move. Indeed, the asthenosphere can move under the effect of thermal convection, which the lithosphere cannot do due to its rigidity. So, to accommodate the asthenosphere's movements, the lithosphere has split into large tectonic plates. Let's take a closer look at the plate tectonics model. This model was developed to explain the global dynamics of the Earth's lithosphere. It all began with the concept of continental drift. The continental drift hypothesis is quite old. It was suggested as early as the late 16th century, although it was German geophysicist Alfred Wegener who really popularized the theory in the early 20th century. According to continental drift theory, today's continents have not always occupied the same place on the Earth's surface. 250 million years ago, they were united in a single primitive continent, Pangaea. Pangaea then fragmented, and the continents drifted to their present positions. How did scientists come up with this theory? First, by observing the coastlines of the continents on the globe. We simply realized that if we brought certain continents closer together, they would fit together a little too perfectly. As you can see from this map, this is particularly true of South America and Africa. The two continents could very well fit together. Their coastlines are very similar. The most logical explanation is that these two continents were once part of the same block, which then fragmented into two parts, both of which eventually drifted apart. Thus, the theory of continental drift took shape. It seemed that the continents were moving horizontally in relation to each other, much as if they were drifting. But how to prove it? Several elements seem to confirm this theory. For example, similar fossils were observed on both sides of the oceans, such as the Sinognathus, a predatory land reptile that lived 240 million years ago, fossils of which have been found in South America and Africa. But it was the acceptance of the plate tectonics model in the late 1960s that finally confirmed continental drift. In 1962, American geologist Harry Hess used the theory of continental drift to develop a model of ocean floor expansion, now known as the conveyor belt model. This model explains the birth and recycling of oceanic crust in the manner of a conveyor belt, as we saw at the start of our journey to the center of the Earth. Oceanic crust is created at ridges, then buried in ocean trenches by downdrafts. It is continually recycled while continental crust drifts along the Earth's surface. Because while continental crust may seem heavy to you, it's actually light compared to the Earth's other layers. This model has been better received than the continental drift model. In this model, the engines of drift are no longer the continental blocks, but the oceans. The continental blocks are passive, driven into the drift by the oceans. This double ocean conveyor belt model was later integrated into the plate tectonic model. This is the model that is universally accepted today. The lithosphere is subdivided into tectonic plates, or lithospheric plates. These plates vary in size and shape. Their characteristics have naturally evolved over geological time as a result of collisions and continental openings. Some plates have split, while others have welded together, forming larger plates. Today, 95% of the lithosphere is divided into 7 major tectonic plates, but there are 46 smaller ones. Here are the 7 major tectonic plates in order of size: the Pacific Plate, the Eurasian Plate, the African Plate, Antarctic Plate, the Australian Plate, North American Plate, the South American Plate. The Pacific Plate is currently the largest. It measures 103 million square kilometers. The Pacific Plate is surrounded by subduction trenches into which it plunges to be recycled into the Earth's mantle. Eventually, this plate will disappear. This also means that the Pacific Ocean will disappear too. Rest assured, we're talking in terms of hundreds of millions of years. This major change in our cartography should give rise to a new supercontinent, now known as Amasia. Although it is difficult to estimate the speed at which these plates are moving, it has been estimated that the Pacific Plate is also the fastest. It is moving 10 centimeters or 4 inches per year northwestwards. This is fast compared to the Australian Plate, which is moving 7 centimeters or 2.7 inches northwards per year, or the Eurasian and American plates, which are moving less than 3 centimeters or 1 inch per year. The movement of the African and Antarctic plates is even more surprising, as they rotate on themselves. Tectonic plates therefore have a variety of relative movements. They collide, move apart, slide against each other. They can converge, diverge, or transform. The speed of relative movement between 2 neighboring tectonic plates varies between 0 and 100 millimeters per year. Geological phenomena such as earthquakes volcanic activity, the formation of ocean trenches, and mountain building occur at the boundaries of these plates, depending on their relative movements. Earthquakes, for example, are produced by collisions between two tectonic plates. In fact, it's thanks to earthquakes that we can define the contours of tectonic plates. If you look at a seismicity map, you'll see that earthquakes are located along lines surrounding non-seismic surfaces, which correspond to the plates. Logically, the biggest earthquakes occur where the plates are the fastest. Mountains, on the other hand, are created by the collision of two continental plates. In this case, the forces involved are so powerful that the plates deform, even though they are rigid, a bit like a head-on collision between two cars. This is how mountain ranges such as the Alps and the Himalayas were formed. The movements of tectonic plates are the expression of convection movements within the Earth's mantle, allowing the Earth to dissipate its internal heat towards the surface. A well-oiled system that works as follows. At the Earth's core, weakly radioactive rocks decay and generate heat. Certain areas of the mantle then become hotter and begin to rise towards the surface. The hotter the zone, the less dense it is, and the more it will rise under the effect of Archimedes' force. This zone will then cool down at the surface, while evacuating some of the heat produced inside the Earth. Once it is cooled sufficiently, it will sink back into the depths, again by the same mechanism. The ridges are zones where matter rises, while it sinks in the subduction zones. Matter is then transferred from the ridges to the subduction zones. It is this movement that gives rise to plate tectonics, and hence continental drift. It's impressive to think that every moment in every ocean around the globe, new oceanic crust is being built up bit by bit, while old oceanic crust is swallowed up by the bowels of the Earth to be recycled. This construction of new crust is called oceanic accretion. At oceanic ridges, the tectonic plates move apart, and the resulting faults are instantly filled with magma from the mantle. Millimeter by millimeter, the plates move away from each other, like scars that magma sutures by filling the voids. This phenomenon creates astonishing structures, such as pillow lava. Pillow lava is formed when lava gushing from the Earth's bowels instantly hardens on contact with icy water. As the lava gushes out, the cushion lengthens. When pressure increases, some cushions burst. Ocean ridges are also dotted with smoking vents. Water that has infiltrated the seabed is heated by the molten magma and bubbles to the surface. In these vents, the water can reach temperatures of 400 degrees Celsius, or 752 degrees Fahrenheit. Their plume can project particles hundreds of kilometers away, and the minerals released can sculpt chimneys up to 55 meters, or 180 feet high. At the same time as these astonishing formations are being created, the ocean floor is widening and the continents are receding. This process is invisible because it takes place far from our coasts, in the depths of the planet's great oceans. And yet, in early 2024, seismologists on Vancouver Island, on Canada's Pacific coast, recorded unusual seismic activity. At the Endeavour hydrothermal site, some 240 kilometers, or 150 miles off the coast of Vancouver, almost 2,000 earthquakes a day were recorded in early March 2024. These quakes, which occur at the Juan de Fuca Ridge, are small earthquakes that went unnoticed by Vancouver residents. But for researchers, they're a godsend, an opportunity to study ocean accretion, or the building of new oceanic crust, up close. The data we'll be collecting will be invaluable. They'll give us a better understanding of the mechanisms by which magma rises from the Earth's mantle, and above all, how oceanic crust is built up. While plate tectonics still conceals many secrets, it is far from being the mystery it was 60 years ago. Today, we are able to reconstruct the movements of tectonic plates that took place millions of years ago, even before the era of the dinosaurs, thanks to modeling software. On the other hand, while we can predict the probability of occurrence of earthquakes along oceanic faults, it is impossible, given our current state of knowledge, to predict major earthquakes. Our continents are not here by chance. The upwelling of magma from the Earth's mantle towards the oceanic ridges, plate tectonics, continental drift, the recycling of oceanic crust beneath the mantle, it's all part of an extremely well-oiled cyclical system, an impressive mechanism. How did such a system come into being? To understand this, we need to go far back in time to the origins of our planet. We're going to go back several billion years to understand how the Earth was formed and how all these successive layers appeared. It's 5 billion years ago. Earth does not yet exist. At the edge of the Milky Way, there is only a vast cloud of gas and dust created by the explosion of a supernova. This molecular cloud, or nebula, is immense. It extends over several hundred light-years in diameter. It's made up of the debris of stars from a primitive universe that exploded after consuming all their energy. The explosion of these stars released particles throughout the galaxy, in particular, heavy elements such as iron, nickel, and aluminum. These particles will come together under the effect of gravitational force to form stars and planets. This is known as particle accretion. Over a period of 10 million years or so, the particles agglomerate, and the dust cloud slowly compresses under the effect of gravity. This compression gradually increases its rotational speed. The addition of matter warms the center of the cloud and releases energy. The cloud begins to form a disk, or rather a rotating ball. This will soon become a star, the Sun. Fast forward in time, it's now 4.6 billion years ago. The Sun is born. The rest of the cloud, which did not agglomerate to form the Sun, is what we call the solar nebula. Particle accretion has also led to the formation of larger objects, known as planetesimals. A planetesimal is a celestial body formed in a disk of debris. It is, according to one of the current theories of planet formation, the first brick in forming a planet like our Earth. The planetesimal measures a few meters to a few dozen meters in diameter. Several planetesimals then gravitationally attract each other to form protoplanets. This is the birth of the solar system. The whole process is thought to have taken between 10 and 15 million years. Today, this is thought to be how stars are formed. At the origin of every star is a vast region of gas and dust called a nebula. These nebulae, are made up of small grains of dust dispersed into a gaseous mixture, rather like lumps. The small dust grains condense, concentrate, and set in motion under the effect of gravitational forces. Gradually, they will take on the shape of disks, at the center of which stars will form. But how did the dust grains of the solar nebula evolve into planets as complex as our own? We'll get to that. We're still in our solar system's past, 4.5 billion years ago. Dust grains from the solar nebula are drawn into the sun's orbit. As these dust grains orbit the sun, they gradually attract each other and coalesce into celestial bodies of varying sizes, from pebbles to planets. According to the planetesimal hypothesis, the accretion of particles first forms planetesimals, which then attract each other and agglomerate to form protoplanets. This is how our planet came into being. Do you find it hard to understand how these grains of dust, even when agglomerated, could form a planet as complex as ours? Scientists have also asked this question. In March 2003, astronaut Donald Pettit carried out an informal experiment in the International Space Station to understand how dust from the solar nebula could give rise to planets. Donald Pettit amused himself by observing salt packets in the weightlessness of the space station. And indeed, the salt packets exhibited some rather amusing behavior. When two salt crystals collide, this creates an electrostatic charge that causes them to clump together. If you shake the salt sachet, the resulting cluster will disintegrate. But if you stop shaking it, it will automatically reform. The same thing happened with the dust particles in the solar nebula. Under the effect of gravity, they agglomerate into disk clusters, forming more complex celestial objects. So, 4.5 billion years ago, the Earth was just a pile of dust. This cluster then grew large enough, around 800 meters or 2,600 feet in diameter, to be able to suck up the dust present in the surrounding disk. Over a period of around 3 million years, the dust clusters of the inner solar system coalesced to form some 20 protoplanets. These protoplanets then collided and coalesced to form the rocky planets we know today: Venus, Mercury, Mars, and Earth. Our Earth would have taken 30 million years to form. What remained of the original cloud formed the asteroid belt, from which almost all meteorites originate. Meteorites, in fact. Meteorites played a major role in the formation of the Earth, from protoplanet to life-supporting planet. For 500 million years, the Earth was subjected to an intense bombardment of other celestial bodies, meteorites and asteroids. In the end, these random and repeated impacts were beneficial, releasing a great deal of energy in the form of heat. The young Earth became overheated. Its temperature reached almost 4,700 degrees Celsius, or 8,500 degrees Fahrenheit. This intense heat melted all the Earth's constituents. At this time, we have a magma planet with no continents or oceans. In other words, the primitive Earth was, at this stage, made up entirely of molten matter. Gradually, however, it cooled. According to the mechanism we mentioned at the start of our journey, the lighter elements will rise to the surface, while the heavier elements, such as iron, will sink into the bowels of our planet. It's now 3.5 billion years ago. The inner core is beginning to solidify. On the Earth's surface, intense volcanic activity, combined with repeated asteroid and meteorite impacts, will emit gases. These gases will form the Earth's future atmosphere. This atmosphere is precious to us. It protects us from the sun's harmful UV rays and maintains a pleasant temperature on our planet's surface. But we're still far in the past, and the primitive atmosphere we're talking about is still very different from our current one. The Earth continues to cool little by little. Now, 50 million years old, it reaches a temperature of 1100 degrees Celsius or 2000 degrees Fahrenheit. It will then collide with another protoplanet. To give you an idea, the size of this protoplanet has been estimated to be roughly equivalent to the current size of Mars. Once again, this collision will provoke a shock that will heat up the Earth and melt it. It was also this collision that led to the formation of our only satellite, the Moon. Residual rock is ejected from the Earth during the collision and clumps together, forming the Moon. At the time of its formation, the Moon was much closer to the Earth than it is today. Its presence will create a tidal effect. This collision didn't just heat up the Earth and make the Moon appear. It is also likely to have altered the Earth's axis of rotation. This tilt is at the origin of the seasons. In the end, it's a good thing the Earth collided with this protoplanet. Without it, we might not have tides and seasons. It was also this collision, after all, that determined the Earth's organization into several layers, or differentiation. The two colliding objects each had their own core. On impact, the two cores fused to form a single core. The Earth's surface remained molten for thousands of years, forming a magma ocean at least 1,000 kilometers or 620 miles deep. Silicate melting produced a silicon-depleted magma. The denser silicate residual solids formed the lower mantle. The even denser liquid iron-nickel alloy migrated towards the center, incorporating silicon and oxygen along the way. This migration took place slowly over 1 million years. All elements with a strong affinity for iron, such as platinum, gold, iridium, and tungsten, were also drawn to the Earth's center. When the upper mantle melted, most of the gases escaped, contributing to the formation of the atmosphere. Once this primitive differentiation was complete, the Earth was made up as follows: a liquid core approximately 3,400 kilometers or 2,100 miles in diameter, a lower mantle 1,900 kilometers or 1,200 miles thick, an upper mantle in the form of a magma ocean around 1,000 kilometers or 620 miles thick. All was not yet one. Barely formed, this primitive Earth was already threatened by a powerful solar storm. Fortunately, the Earth's core created a magnetic shield through the dynamo effect. This is known as the magnetosphere. This extra layer acted as a veritable shield. At this stage, the Earth already has a core, a mantle, and a primitive atmosphere, probably made up of rare gases, such as neon, argon, or krypton, its atmosphere still contains very little helium, nitrogen, and carbon dioxide, but it still has no crust or water. At this point in Earth's history, the inner solar system is still far too hot for water to exist in a liquid state. What's more, the materials that make up the early Earth don't contain enough hydrogen to form water. The core and mantle were therefore the first layers to form. The core formed at the same time as the Earth by accretion 4.56 billion years ago. The fusion of the primordial materials that make up the Earth, meteorites, planetesimals, and protoplanets, led to the formation of a global ocean of magma, then to the differentiation of the Earth into several layers. The silicate or rocky part became the mantle. The mantle is depleted in elements with an affinity for iron, or siderophiles, which were absorbed by the core. And how in all this was the Earth's crust formed? Even after the global differentiation of the primitive Earth, meteorite bombardments continued. Traces of this can still be found on the Moon. On Earth, these bombardments erased all traces of the formation of the Earth's first crust. However, we can still date its formation to 4.47 billion years ago, or 100 million years after the start of the solar system. As for water, there are a number of hypotheses as to how it came to be on Earth. The current hypothesis is that half of all water was brought to Earth by a meteor shower from outside the asteroid belt. Comets contain 50% water, and this water contains twice as much deuterium as terrestrial water. The other half of the water would have appeared with the outgassing of the mantle. By mixing these two types of water, we could have obtained the quantity of deuterium corresponding to the isotopic signature of terrestrial water. This raises another question. What could have caused the meteor shower that brought water to Earth? It is thought that 4.1 billion years ago, when the solar system was still young, Jupiter and Saturn found themselves in 2-to-1 gravitational synchronicity. This means that for every orbit Saturn completes around the Sun, Jupiter completes too. This created ripples through the debris disk surrounding the Sun, propelling Uranus and Neptune into more distant orbits. This great planetary move had far-reaching repercussions, destabilizing the Kuiper Belt and sending a shower of asteroids and comets through the inner solar system. As these meteorites collided with the Earth, they disintegrated and released water. As a result of this massive collision, oceans were formed. The formation of oceans would therefore have been relatively rapid, contrary to long-held belief. They would have taken around 150 million years to form. These oceans were then rich in iron and green. To say the least, the primitive Earth didn't look much like the Earth we know today. In addition to its reddish hue, caused by a very dense atmosphere rich in nitrogen, carbon dioxide, and methane, the Earth was hotter, with an average surface temperature of 93 degrees Celsius, or 200 degrees Fahrenheit. Gradually, however, the meteorite bombardment slowed down. By observing the oldest living fossils, stromatolites, which were present some 3.5 billion years ago, scientists have been able to trace the evolution of the Earth's primitive oceans. stromatolites can be seen in the Pilbara region of Australia. These cyanobacteria use carbon dioxide and light to release oxygen. However, models have shown that there was no accumulation of oxygen in the atmosphere during this period. Why is this? It's thought that the oxygen released by stromatolites and later by cyanobacteria reacted with iron to form iron oxide. The first oceans saturated with iron would then have absorbed this oxygen for 1 billion years. Until around 2.5 billion years ago, the iron in the oceans was completely oxidized. The oxygen then began to accumulate in the atmosphere. Over the next 2 billion years, the level of oxygen in the atmosphere increased, finally reaching, 500 million years ago, the level needed to form an ozone layer intense enough to allow the first plants to emerge from the water and colonize land. We know how water appeared on Earth, but we're still a long way from the continents and oceans of today's Earth. Remember that at this stage we're still on a magmatic Earth. Chemical elements come together and are distributed according to their mass, depending on gravity. As a result, the heaviest elements are migrating towards the center of the planet. Iron and nickel in particular migrate towards the core. At present, the core is made up mainly of iron and nickel, with a few siderophilic elements. As for the lighter elements, they migrate towards the mantle. Gradually, the Earth grows in size and pressure increases. The mantle solidified, as did part of the core, the solid inner core. The origin of the first continents can be traced back to this solidification of the mantle 4 billion years ago. Then plate tectonics set in, and you know the rest. The single terrestrial continent of Pangaea, which appeared around 200 million years ago, then split into 2, then 5 pieces. Then, over millions of years, the continental blocks migrated to their current position. But on Earth, nothing is immutable, and in a few million years, the continents won't be at all the same as they are today. Recently, an international team of researchers even discovered a sunken continent, hidden beneath Iceland, which is believed to be its emerged part. This new continent, or rather this rediscovered ancient continent, has been christened Icelandia. Icelandia is thought to be an ancient piece of Pangaea, which instead of breaking up, stretched out like chewing gum, becoming thinner. As for the formation of today's oceans, it took place at the same time, always very gradually. It was when the temperature of the Earth's atmosphere cooled considerably, dropping below 100 degrees Celsius, or 200 degrees Fahrenheit, that water was able to become liquid. But for millions of years, water reaching the hot ground could not remain in a liquid state. So the water vaporizes, rises into the atmosphere as it cools, condenses again, and falls as rain. A repetitive cycle that with patience eventually formed reservoirs of liquid water on the Earth's finely cooled surface. The water trickling down the primitive Earth's young relief eventually accumulated in the hollows of the crust, first in pools, then in lakes, then in seas and oceans. New scientific studies regularly reveal new aspects of the Earth's formation history. Not only have new continents recently been discovered that we didn't even know existed, but new facts about the history of the appearance of continents have also been revealed. In 2017, scientists discovered traces of an extinct continent deep in the waters of Mauritius. In 2019, the continent of Icelandia was discovered, submerged beneath Iceland. In 2020, geologists from Monash University examined the process of continent formation over the course of the Earth's 4.5 billion year history. Once again, they discovered some fascinating facts. According to this team of researchers, continents spent 500 million years solidifying. Between 4.5 and 4 billion years ago, the continents were in their infancy. They were still fragile and prone to destruction. It was only gradually that they solidified to form the skeleton of today's continents. This is a novel way of looking at the appearance of the first continents, and it explains many things. In particular, it explains why we still find traces of continents that were lost and swallowed up by our present-day continents. This period in the Earth's history, when continents were weak and malleable, has a name: the Hadean. In 2023, a study by researchers at Curtin University, Australia, published in the journal Earth Science Reviews, investigated the question of how our continents appeared. The researchers went back as far as 3.2 billion years ago, when plate tectonics completely changed the appearance of our planet. In fact, the Earth's mantle is rich in minerals whose dating helps us to understand the emergence of the first continents. Lead and zinc deposits, for example, are between 3.4 billion and 285 million years old. This corresponds to the period when the first continents appeared. 3.2 billion years ago, it would appear that these ores then contained in the Earth's mantle took on a different form and differentiated from the mantle. This marked the beginning of plate tectonics, and hence continental movement. Nearly 3 billion years ago, the original continents would have merged into a single supercontinent, Pangaea, before breaking up again under the effect of plate tectonics. We're almost at the end of our journey to the center of the Earth. You're now familiar with the Earth's internal structure, divided into successive layers, from the crust through the mantle to the core. You know the particularities of each layer: the continental and oceanic crust, the lithosphere, the asthenosphere, the upper and lower mantle, the liquid outer core and the inner core. You also know when and how the Sun, the Earth, its core, mantle, oceanic crust and continents were formed. But this knowledge is never static. Our knowledge of the Earth's internal structure continues to evolve as new discoveries are made. Lately, there's even talk of revising the Earth's internal structure by adding an extra layer. In 2021, researchers studied the Earth's internal structure several thousand kilometers below the surface. They made a surprising discovery, reported in the Journal of Geophysical Research. The Earth could be made up of 5 layers, not 4 as previously thought. This 5th layer would be located in the Earth's inner core. It would be in addition to the 4 layers on which all scientists agreed: the crust, the mantle, the outer core, and the inner core. The idea of a 5th layer has been proposed for decades. So in itself, this discovery is nothing new. But this time, the data are clear enough to constitute proof of the existence of a 5th layer. The discovery was made with the help of an algorithm. It reviewed a huge amount of data from seismic events over the last few decades. The data was then compared with the current model of the Earth's structure, a mammoth task made possible by technology. The scientists realized that for the two to be in perfect agreement, a fifth layer would have to be present, located in the Earth's inner core. While it is not yet known how this fifth layer would have formed, this discovery has definitely been the starting point for more in-depth studies. A study published in February 2023 in Nature Communications brought the subject back into the spotlight. Two seismologists revealed new evidence supporting the hypothesis of a deeper inner core. According to the results of their studies, this core would be 644 kilometers, or 400 feet thick. To determine this, they studied the seismic waves generated by earthquakes crossing the Earth's diameter. It appears that earthquake shock waves reverberate at different speeds in what could be a fifth layer. Like the rest of the core, this layer is made up of an alloy of iron and nickel. The difference? It has a crystalline structure. This core could have formed following a major global event in the past, such as a shift in plate tectonics. This event would have occurred hundreds of millions of years ago. The debate is always lively, but above all, it's extremely exciting. The answer is eagerly awaited. The discovery of a fifth layer could help us understand even better how our planet was formed. Did you know that 90% of the Earth's magnetic field originates from the center of the Earth, more precisely from the liquid outer core? The Earth's rotation causes vast vortices in the liquid outer core. These movements generate an electric current, and therefore a magnetic field, a bit like a bicycle's dynamo. It is possible for the magnetic field to reverse. In any case, this has already happened in the past. The magnetic field has reversed around 300 times over the last 200 million years. The last reversal was 780,000 years ago. If the magnetic field reverses, the North Magnetic Pole will end up at the South Pole. It's impossible to predict when the magnetic field will reverse, but scientists are increasingly convinced that it will happen soon. Over the past 15 years, the North Magnetic Pole has been moving faster and faster from northern Canada towards Siberia. In 1970, it was moving 10 kilometers or 6 miles per year. By 2003, it had reached 40 kilometers or 25 miles per year. Today, its speed has increased to 60 kilometers or 38 miles per year. The European Space Agency's SWARM mission aims to determine the date of the next inversion. However, don't panic. We think that if there is an inversion of the Earth's magnetic field soon, it won't be in this century. So we won't need to change our compasses for a long time. By the way, why can't we produce the next inversion of the Earth's magnetic field? The magnetic field is a complex concept. The convective motion at the origin of the magnetic field in the Earth's bowels depends on many factors: temperature variations, depth, the Earth's rotation. What's more, the Earth's magnetic field is not dipolar, but multipolar. The two magnetic poles, north and south, are not located on opposite sides of the Earth, since the North Pole moves faster than the South Pole. Added to this are the magnetic anomalies found in volcanic rocks. Some are magnetized in the same direction as the current magnetic field, while others are magnetized in the opposite direction. What's more, observing periods of magnetic field inversion has not enabled scientists to identify patterns. The reversals are neither regular nor of equal duration. Their frequency is chaotic. What we do know is that our reversals occur in the short term over periods of 1,000 to 20,000 years at most. But that's not much, and above all, it's not enough to predict an upcoming inversion. We've come to the end of our journey to the center of the Earth. During this journey, you have been able to discover the particularities of each layer that makes up the heart of our planet, from the continental crust to the iron core. Layer by layer, we unveiled the peculiarities of our planet's internal structure and the mysteries it still conceals. Our knowledge is still uncertain, as it is based on indirect observations via the propagation of seismic waves or rocks brought up from the depths of the Earth. It's certain that in the future we'll continue to discover other hidden features of our planet's interior, which will represent ever more windows onto its past and history. The collision of two galaxies is an ordinary phenomenon in the evolution of galaxies. It occurs when two galaxies collide at sufficient speed to merge. The gas and dust of the two galaxies will then interact. The interstellar medium is disturbed and heated. This shock can trigger a starburst, also known as a starburst galaxy, in one of the two galaxies. This phenomenon generates an exceptional rate of star formation in one of the galaxies. These bursts are temporary, because if the rate of star formation were to remain so high, the reservoirs of star-forming gas would be completely dissipated much faster than the dynamic lifetime of the galaxy. The stars in the two galaxies, meanwhile, generally don't collide with each other, as the distances between stars. A starburst is generally defined by three factors: the star formation rate, which is the rate at which the galaxy will convert gas into stars, the amount of gas available to form stars, and the comparison between the star formation period and the age of the galaxy. For a starburst to occur, a large quantity of molecular gas must be concentrated in a small volume. This usually occurs during galaxy mergers. Categorizing the various starbursts is not straightforward, as not all galaxies share the same specific characteristics. Starbursts can occur in the galactic disk or be scattered throughout the galaxy. Nevertheless, astronomers are currently discussing a number of classes. The subtypes of starbursts currently defined are blue compact galaxies, infrared luminous galaxies, and Wolf-Rayet galaxies. Compact blue galaxies have low mass and low metallicity. Dust-free, they contain a large number of relatively young hot stars. As a result, they are luminous in the blue and ultraviolet. Astronomers initially thought these galaxies were young, but old stellar populations have been found in a number of them. In addition, the majority of compact blue galaxies show evidence of recent interactions. Infrared luminous galaxies are characterized by extremely high dust concentrations. They emit a red color because the ultraviolet radiation they emit is absorbed by dust and re-emitted as infrared. Most of the infrared luminous galaxies observed show a double core system. This suggests that star formation may have been triggered by galaxy mergers. In Wolf-Rayet galaxies, the majority of bright stars are Wolf-Rayet stars. These hot stars, with masses equivalent to several tens of solar masses, will start expelling matter in the form of high-speed stellar winds during a brief phase. A starburst has a large gas reserve. Collision with another galaxy triggers the starburst itself. Inside the starburst, the environment is extreme. Massive star formation generates large quantities of gas. One of the most famous starburst systems is the Antennae galaxy. The Raven constellation is one of the 48 constellations listed by the astronomer Ptolemy. It lies close to the constellation Virgo to the north and east, Hydra to the south, and Cup to the west. The Raven constellation has few bright stars. Its 4 brightest stars are Gamma, Beta, Delta, and Epsilon. Gamma, with a magnitude of 2.59, remains the brightest. These 4 are easy to spot in the night sky, as they form an unusual quadrilateral. However, the most striking celestial objects in this constellation are not these stars, but 2 galaxies that are currently on a collision course, the Antennae galaxies. Also known as NGC 4038 and NGC 4039, the Antennae galaxies are an emblematic example of galactic collision. While pairs of interacting galaxies are quite common in the universe, it's rarer to witness the spectacle offered by NGC 4038 and NGC 4039. According to scientists, the collision began 600 million years ago. The Antennae galaxies were originally 2 spiral galaxies. NGC 4038 is very large and lies at a Hubble distance of around 95.2 million light-years. It is also defined as a star-forming galaxy. It has an exceptional rate of star formation compared with other observed galaxies. This phenomenon represents just one stage in the life of a galaxy, and is certainly due to the interaction with NGC 4039. The phenomenon is therefore limited in time. The interaction of the Antennae galaxies in the night sky is a veritable firework display, illuminating thousands of nebulae and young star clusters. It's a spectacle of unspeakable beauty. The arms of the galaxies were deformed and the cores brought close together. The impact sent out 2 immense jets of stars and gas, earning this celestial duo the nickname the Antennae. With a 100mm aperture, it's possible to observe the galaxy duo, which appears as a diffuse spot with no detail. When viewed through a 200mm telescope, the dual nature of the object becomes clear. Its shape takes on the appearance of a V elongated towards the west. But it's only when you use 300 to 400mm instruments that the spectacle becomes striking. The 2 Antennae galaxies form a magnificent, asymmetrical boomerang. NGC 4038 to the north represents the brighter, more curved part, while NGC 4039 to the south is thinner. Astronomers believe that within 400 million years these 2 galaxies will have merged. For us, this gigantic timescale is nothing compared to the lifetimes of these stars. This collision could give rise to a larger galaxy, perhaps of the elliptical type. The nearest ultra-bright infrared galaxy is ARP 220. It is located around 245 million light-years from the Milky Way, in the constellation of Serpent. ARP 220 is the result of the collision of 2 galaxies that are currently merging into one. ARP 220 radiates mainly in the infrared. Most of its luminosity comes from the intensive formation of young stars, since it is a star-forming galaxy. Scientists have observed over 200 stellar clusters at the heart of this galaxy, some reaching masses of the order of 10 million solar masses. ARP-220 has an active galaxy core. This core is characterized by a compact region at the heart of the galaxy. Its luminosity is higher than average and not of stellar origin. In theory, it results from accretion by a supermassive black hole. The Whale constellation is the fourth largest constellation in the sky. Its best-known stars are Mira and Difta. Within this constellation lies the ARP-147 system, also known as the Ring Train. This pair of colliding galaxies lies 440 million light-years from Earth. The Ring Train perfectly represents the most spectacular effects of galaxy collisions. The two galaxies making up the pair are considered special galaxies in that they are neither elliptical, spiral, barred spiral, nor lenticular. They are, however, regular in shape. The two galaxies are shown, one in profile, evoking the number 1, and the other from the front, appearing to represent the number 0. Together they form a gigantic 10. This extraordinary figure in the sky is the result of an extremely violent collision. The galaxy on the left, representing the number 1, has smashed right through the galaxy on the right, representing the number 0. In the same way that a pebble emits a wave when it comes into contact with water, the collision created a wave at the point of impact. This density wave traveled outwards through the affected galaxy, colliding with the stars, gas, and dust as they tumbled towards the center, under the effect of an increased gravitational force. As a result of the collision, the high-temperature matter clumped together, stimulating the formation of young stars. A red spot can be seen at the bottom of the right-hand galaxy forming 0. This is probably the remnant of the galaxy's nucleus after the collision. Made up of around 50 individuals, the local group is a very modest cluster in which our galaxy, the Milky Way, lies. Nevertheless, its evolution has been as tumultuous as that of larger galaxy groupings. Based on the stigmata found on the Andromeda Galaxy, also known as M31, numerical simulations have attempted to reconstruct its past. At present, M31 is the only galaxy in the local group larger than the Milky Way. 5 billion years after the Big Bang, the local group is made up, in addition to the future Milky Way, of two rather large galaxies, one of which is 4 times more massive than the other. Their relative proximity generates a mutual attraction that brings them closer together, until they inevitably collide 4 billion years later. The merging of these two galaxies gives rise to the Andromeda Galaxy. The distances between the stars of the two galaxies are so great that another head-on collision is ruled out. Tidal forces create a gigantic trail of stars. Part of it returns towards the larger galaxy, the result of the ongoing merger, while the other part escapes the latter's grasp and gathers into two dwarf galaxies known as the Magellanic Clouds. Their speed is such that they soon find themselves close to the Milky Way. Supernovas are spectacular events marking the end of the evolution of a massive star. During these gigantic explosions, the energy released in a few seconds is comparable to that emitted by a star throughout its lifetime. The phenomena triggering these explosions vary, according to whether the star belongs to a binary system or to a single star. In the latter case, a supernova explosion will only occur if the binary system's companion star is a white dwarf. Under certain conditions, the white dwarf is gravitationally bound to its companion star, absorbing matter from the latter's surface layers. the captured material falls onto the white dwarf and heats up. When it exceeds the mass limit at which a nova is formed, nuclear reactions are set in motion until it is destroyed. In the case of an isolated star, the star itself explodes once all internal nuclear fusion cycles have taken place. Gravity then takes over, and the star contracts very rapidly. The resulting heating triggers uncontrolled nuclear reactions in the core. An explosion occurs, releasing enough energy to destroy the star. The explosion leaves behind a trace called supernova remnant. This is an expanding cloud of gas. Astronomers identify supernovas by their characteristic light curve. They exhibit a rapid increase in luminosity that lasts several days. When this luminosity reaches a maximum, it stabilizes for around 10 days. It then decreases discontinuously, followed by a steady decline. Interpretation of the light curve enables us to study the evolution and dynamics of the explosion. Because of their extreme brilliance, supernovae are one of the favorite objects of astronomy enthusiasts. And it's thanks to them that around 50 supernovas have been discovered every year since 1990. Several supernovas have left their mark on the history of astronomy. On February 24, 1987, Canadian-born astronomer Ian Shelton set out to take long-pause photographs of the Large Magellanic Cloud, a dwarf galaxy close to the Milky Way, visible from the southern hemisphere. While developing his photographs, he was surprised by the presence of a new star. After consulting several colleagues, he discovered that the star had also been seen by others. The first traces of the explosion to reach Earth were carried by neutrinos, which are difficult to detect particles emitted rapidly, in very large numbers, shortly before the star's increase in luminosity. SN 1987A was the first supernova explosion of the 20th century to be observed by the naked eye under optimal observing conditions. It provided crucial data for understanding the mechanisms of these stellar explosions. The general principles governing the supernova phenomenon have been confirmed. Studies clearly show that 99% of the energy emitted by supernovas is in the form of neutrinos. But for the first time in 1987, thanks to the supernova explosion, neutrino emission was observed instantaneously. When the star's core collapses under the effect of gravitation, electrons merge with protons to form neutrons and neutrinos. The latter interact very little with matter and are immediately released. Another feature of SN 1987A is that the star that gave rise to it was a blue supergiant. The presence of 3 gas rings around the supernova made it possible to understand that the star had evolved from a red supergiant to a blue supergiant around 20,000 years before the explosion. This progenitor star is called SK 69202, or Sandelic 69 degrees 202a. It was born 10 million years ago with a mass 20 times that of the Sun. Astronomers were surprised that it was a blue supergiant rather than a red one, as it was suggested at the time that only stars in the red supergiant stage evolved into supernovas. Today, the supernova afterglow remains the focus of numerous observations, even if the search for the compact residue has so far been unsuccessful. Thanks to numerous instruments on the ground and in space, the supernova has been observed continuously, both in terms of electromagnetic radiation and by neutrino detectors. The phenomenon occurred at a distance of around 51.4 kiloparsecs from our planet. In May 1987, it reached its maximum brightness with an apparent magnitude of around +3. Supernova 1993J occurred in galaxy M81 in 1993. It was discovered by a Japanese amateur astronomer and was one of the brightest supernovas of the 20th century. Its ancestor has been identified as a K-type supergiant star, characterized by an excess of ultraviolet light, which may be due to the surrounding hot stars or a hot binary companion. SN 1572, also known as Tycho's supernova, is a supernova in the constellation Cassiopeia, 7,500 light-years from Earth. It owes its name to the Danish astronomer Tycho Brahe, who first observed it on November 11, 1572. On that day, it appeared much brighter than Venus, with an apparent magnitude of -4. It wasn't until March 1574 that its brightness dropped below the threshold of visibility to the naked eye. This supernova became one of the most famous events in the history of astronomy, since it contradicted the Aristotelian theory of the inalterability of the cosmic world. Indeed, since ancient times, the world beyond the moon had been considered unshakable. For scientists of the time, it was only between the Earth and the Moon that new celestial objects could appear. Tycho Brahe's discovery implied a new object much further away. Over the course of months of observation, he also discovered that the object had not changed position relative to the fixed stars, and could therefore not be a planet, but another star. In 1573, Tycho Brahe published his discovery, calling it a new star. This revolutionary expression turned astronomy on its head. It led to the development of better astronomical classification catalogs and improved observational instruments. The supernova's progenitor star was probably a dwarf that had drawn in matter from another companion star until it exploded. Type 1 supernovas, like SN 1572, do not involve the formation of extraordinary nebulae. That's why its faint afterglow was only discovered in the 1960s. Thanks to the Chandra Space Telescope, astronomers were provided with astonishing images of Tycho's supernova. These showed lumps in the remains of the star, as if several ignition points had existed within the supernova. The explanation is that SN 1572 underwent an asymmetric explosion. The explosion produced a large cloud of expanding debris. A thin blue line, representing ultra-high energy electrons, can be seen around the perimeter. The dust formed is ejected into the cosmos. Numerous other stars adorn the supernova's vicinity, like sparkling white diamonds. SN 1604, also known as the Kepler supernova, occurred in the Milky Way in the constellation of Ophiuchus in 1604. It is a type 1A supernova, or thermonuclear supernova, resulting from the explosion of a white dwarf. In most cases, the latter captures the matter of a companion star until it reaches critical mass and explodes. In the case of Kepler's supernova, however, it appears to have been triggered by the merging of two white dwarfs. As there are no bright stars in the vicinity of the central region of the supernova's remnants. SN 1604 was observed by German astronomer Johann Kepler and was visible to the naked eye for over a year. Kepler was not the discoverer of the supernova, but it was he who carried out the most detailed research on the star. He wrote about it in his book, Sur la nouvelle étoile dans la piède de Ophiuchus, on the new star in the foot of Ophiuchus. This supernova lies at a distance of 20,000 light-years from our planet Earth. Its relatively low position on the horizon and declination of minus 21 degrees could have made it difficult to detect, but certain circumstances were favorable to its discovery. SN 1604 lies in a region where the planets of the solar system circulate. In October of that year, Jupiter, Mars, and Saturn were located in this very zone. What's more, with the Sun at the same time located around 60 degrees west of this region, the sky was easily observable in the early hours of the night. What's more, Tycho Brahe's discovery some 30 years earlier had sparked a great deal of interest among astronomers in observing the night sky. Today, NASA astronomers report that some debris from the explosion is still moving through space at speeds of up to 37 million kilometers per hour. The average speed of the clusters studied is around 16 million kilometers per hour. The 4 fastest clusters in SN 1604 are all heading in the same direction and have a similar chemical composition. This may mean that the debris is coming from a single layer of the progenitor star. These velocities have already been observed in supernovae in other galaxies, but only just after their explosion. In the case of SN 1604, the displacement of its remnants continues unabated, even 400 years later. Astronomers have yet to explain this phenomenon, but several theories have been suggested. The explosion could have been so violent that the material was ejected at very high speed, or the white dwarf's environment is lumpy and the debris made its way along low-density paths without being slowed down. SN 1054, also known as a supernova of the year 1054, is famous for the afterglow it left behind after the explosion, known as the Crab Nebula. It is one of the most studied objects in the sky. The supernova was observed in 1054 and documented by Chinese and Arab astronomers. Numerous written sources attest to the explosion of a star in 1054. At the time, in China, transient stars such as comets, novas, or supernova explosions were called guest stars. Several accounts in official archives of events during certain dynasties relate this phenomenon in 1054. 3 other Japanese texts, individual chronicles, also mention this guest star at the same time. In the Arab world at the time, astronomers were interested in cyclical phenomena, whereas supernova explosions were considered to be atmospheric phenomena. Nevertheless, there is a doctor's account of a spectacular star appearing in the sky. All report that in July 1054, a star began to shine so brightly that it exceeded the brilliance of Venus. It remained visible in daylight for 3 weeks, and in the night sky for almost 2 years. 7 centuries later, in 1758, the famous Charles Messier searched assiduously for Halley's Comet and confused it with a small nebula in the Taurus constellation. To avoid further confusion, he decided to create a catalog of diffuse stars and assign the number 1 to this star. In 1928, Edwin Hubble made the connection between the Chinese astronomer's guest star and the Messier 1 nebula, the expanding cloud of gas released by the supernova of 1054. It's nicknamed the Crab Nebula. This nebula continues to grow at a speed of 1,500 kilometers per second, or 930 miles per hour, and will dilute in space over the coming millennia. Within the nebula remains the compact residue of the exploded star, the Crab Pulsar. The pulsar is less than 1,000 years old. it generates electromagnetic radiation, 100,000 times more intense than the Sun. This is what makes the central part of the Crab Nebula so bright. The nebula and pulsar form one of the most studied structures outside the solar system, as both are among the brightest objects in their respective categories. What's more, the date of the explosion is well known. SN 1054 is the most famous supernova in the history of astronomy. In winter in the northern hemisphere, it can be observed through a small telescope and appears as a pretty gray blob against the stellar background of the Milky Way. Supernova 2014J occurred in galaxy M82 in January 2014. It is a Type 1a supernova, and the closest to it discovered in over 40 years. To date, it remains the brightest supernova observed in the Cigar Galaxy for decades. It has been extensively studied in different wavelengths due to its unusual brightness and proximity. Far less spectacular than Type 2 supernovas, which are the endpoint of massive stars, whose remnant is usually a neutron star, Type 1a supernovas are produced by the explosion of much smaller stars, known as white dwarfs. Their explosions are said to be thermonuclear. At the end of the explosion, all that remains in space is a gigantic jet of particles known as afterglow. The supernova was discovered on January 21, 2014 by chance, while astronomer Steve Fossey was training his students to use a small telescope at the University of London Observatory. The scientists simply wanted to take advantage of a brief gap in London's cloud cover. He and his students then noticed a bright new star in the images taken of the Cigar Galaxy. The discovery was reported to the Astronomical Union's Central Astronomical Telegram Office, which confirmed that they were the first to spot this supernova. At the time of discovery, the supernova was 14 days from its maximum light, suggesting that it would become brighter over the following 2 weeks. It continued to get brighter until January 31st, when it had an apparent magnitude of 10.5. Quasars are the brightest sources of light in the universe. The word quasar comes from an English abbreviation meaning source of quasi-stellar radio radiation. These are extremely distant stars that look like very bright stars when observed through a telescope, but are actually examples of active galactic nuclei. Their impressive energy comes from the accretion of matter by rotating supermassive black holes that can contain millions to billions of solar masses. The black holes that sit at the center of galaxies are of an altogether different caliber to those produced by stars. While the latter sometimes reach the mass of the Sun, galactic black holes are millions, even billions of solar masses. The luminous power emitted by quasars can reach 10,000 times the total luminosity radiated by the hundreds of billions of stars in a galaxy the size of our Milky Way. However, most galaxies are not the site of such a violent outburst. Quasars are thought to gain power through the accretion of matter around supermassive black holes in the nuclei of these galaxies. No other mechanism seems capable of explaining the immense energies released and their rapid variability. But some phenomena remain unexplained to this day. For example, some relatively quiet galaxies seem to suddenly become quasars in just a few months. The remarkable luminosity of quasars is used as a tool for probing intergalactic space right up to the limits of the observable universe. Before reaching our telescopes, the photons emitted by quasars may encounter tenuous clouds of intergalactic gas on their billion light-year journey. Quasar absorption systems provide additional structural information to that provided by the distribution of galaxies. The growing number of known quasars, with their absorption spectra, enables more detailed statistical studies of the distribution and properties of intergalactic gas clouds and their relationship with dark matter and existing or forming galaxies. Absorption systems can be used to probe precise moments distributed throughout the history of the universe, but also to address essential issues in cosmology and even physics. The first quasars were seen as early as the late 1950s, and today there are over 100,000. Quasar 3C273 lies at an astronomical distance of 2.44 billion light-years, 1,000 times further away than the Andromeda Galaxy. It is located in the constellation Virgo. According to Hubble's law, and given its distance, this quasar is moving away at almost 50,000 kilometers per second, or 31,000 miles per second. The black hole at its center needs the equivalent of several hundred times the mass of the Sun per year to feed itself. It discharges some of this matter in the form of an immense jet. When it no longer has enough energy to feed itself, its host galaxy will revert to an ordinary star, and its luminosity will diminish. If there's one object in the universe renowned for its unprecedented violence, it's the quasar 3C186. This double quasar emits waves in all domains of light. It lies in the Lynx constellation, more than 8 billion light-years away. 3C186 lies at the heart of the galaxy, PGC 2817581. It has several special features. Its central light is offset by around 35,000 light-years from the center of the galaxy. This is due to the interaction between 3C186 and the second black hole inside it. The impact of these two supermassive black holes disrupts the galaxy, breaking it up and scattering its stars. The interaction between the two black holes is thought to have taken place 5 million years ago. Astronomers estimate that 3C186 will leave the galaxy in around 20 million years. The result will be two supermassive black holes merging to form a black hole with a mass equivalent to 1 billion solar masses. The Earth has been hit by numerous asteroids. These collisions have played a major role in the history of its formation and evolution. Some 9 billion years have passed since the Big Bang. The local supercluster contains over 10,000 individuals. On its periphery, the local group is made up of some 50 galaxies, including the Milky Way, one of the largest. The Milky Way has a thin disk of stars and gas. This highly diluted gas concentrates in a few places, in much denser spirals. These interstellar clouds are opaque with molecules and grains of dust. One of them wanders proudly 27 light-years from the center of the Milky Way. Then, a fragment of this nebula collapses in on itself. The contraction transforms the globule into a protostar, and its energy into radiation. At its heart, the temperature rises so high that thermonuclear reactions cause hydrogen to fuse. A star is born, but not just any star, our Sun. Before its final contraction, the protostar is surrounded by a disk of gas and dust, which then divides into countless smaller bodies. Some agglomerate into larger structures. Matter spinning too fast to join the Sun in formation takes the form of a disk made up of gas, dust grains, and tiny aggregates of solid matter. The grains gradually stick together until they agglomerate into blocks. Under the effect of gravity, bodies over 1 kilometer in length are formed. The largest of these absorb everything within their sphere of influence. Planetary embryos are born. Their mass increases with distance from the Sun. Below the ice line, the environment is gradually emptied of gas, and the planetary embryos see their orbits lengthen to the point where they can cross each other. Violent collisions ensued, leaving only 4 of the planets, including Earth, intact. Barely scratched out of the ground, the Earth is already experiencing an eventful life. Our planet has cleaned up its orbital zone. The only exception is the 2 Lagrange points, L4 and L5, in the Earth-Sun system, which provide shelter for planetesimals attracted to the Earth during its formation. Point L4, for example, shelters a planetary embryo that continued to develop until it reached the size of today's Mars. Its name is Theia. Having reached too great a mass, Theia became unstable and escaped from its L4 equilibrium point. It then orbits the Sun until it collides with the Earth. Theia is totally shredded. Its pieces scatter all around. Its core, mainly iron, is buried in the heart of the Earth. 24 hours after impact, our future planet is surrounded by a disk of light rock from the 2 planetary mantles that collided. After a few years, these rocks agglomerate to form a new celestial object 20,000 kilometers or 12,500 miles from the Earth, which gradually moves away to become its satellite, the Moon. At first glance, this cosmic collision seems no more exceptional than any other. And yet, by giving the Earth such a large satellite capable of stabilizing its axis of rotation, this collision is paradoxically an essential event in the future evolution of life. The Moon plays a very important role in the existence of life on Earth. It exerts a major influence on the weather, the migrations of certain animals, the Earth's magnetic field, and in many other areas. It is also responsible for the 24-hour day. The Earth's tilt is kept stable by the Moon's gravity. If it weren't for the Moon, our planet would move up and down during its rotation. And if such wild movements were to take place, wind and clouds would move faster, and weather conditions would be extremely harsh and much less conducive to life. The phenomenon of the 4 seasons is also due to these changes in the Earth's rotation and axis. Without the Moon, the Earth would rotate on its axis in 8 hours instead of 24. The Moon's gravity slows down the Earth's movement, with enormous repercussions for the evolution of life on Earth. If a day lasted 8 hours, animal species would have had to adapt to rapid temperature changes and would certainly have evolved very differently. During the Moon's first days, solar winds were much more violent. At that time, the Moon was closer to the Earth, and its magnetic field was sufficient to protect its atmosphere and act as a shield against solar winds. If the Earth had no atmosphere, life as we know it today would not be possible. It contains the oxygen we breathe and protects us from ultraviolet rays and cosmic rays. The effect of the Moon's and Sun's gravity on the Earth slightly deforms the planet from front to back. This is what we call tidal forces, which cause ocean tides. Tides probably propelled the first forms of marine life onto land. Tides may also have influenced the Earth's plate tectonics. It is thanks to seismic activity that the planet's surface was able to cool and become habitable. 4 billion years ago, large-scale meteoric and cometary impacts hit the terrestrial planets. It was during the Apollo 15, Apollo 16, and Apollo 17 missions that this theoretical period in the history of the solar system was brought forward. The landing sites for these missions were established close to the great impact basins of the Sea of Rain, the Sea of Nectar, and the Sea of Serenity. Lunar rock samples were collected, and analysis on Earth revealed that their age ranged from 3.8 to 4.1 billion years, a relatively short period. These data were compared with the dating of other lunar meteorites recovered on Earth. Due to erosion, impact marks of ancient origin are very rare on our planet. Although this has long been interpreted as proof that the Earth's surface remained liquid for a long time, it would appear that in reality, the solidification time was much faster, and that the youth of the Earth's crust is due to the theory of the late Great Bombardment. At the start of the solar system's formation, the 4 giant planets were much closer together than they are today. Uranus is the furthest from the Sun, and lies close to the inner edge of a planetesimal-rich disk. Barely 600 million years after the formation of the solar system, the gas giant planets began to migrate due to gravitational interactions with the famous small objects that remain at the inner edge of the disk. Saturn, Neptune, and Uranus are moving strongly inwards, and Jupiter more moderately. Jupiter's rotation period around the Sun is half that of Saturn. This movement completely destabilized the solar system, and collisions between small bodies and the terrestrial planets increased. It was the beginning of chaos. Saturn was pushed back into its final orbit by Jupiter, and collided with Neptune and Uranus. The latter two are expelled into much more elongated orbits. They plunge into the planetesimal-filled disk, ejecting thousands of planetesimals far from their original orbits. For the most part, these small bodies fly outside the solar system, giving rise to the Kuiper Belt, among others. But some of them head inland. The 4 terrestrial planets, as well as the Moon, are the victims of numerous brutal impacts. The Earth is said to have been hit by 22,000 giant meteorites. Some asteroids were larger in diameter than France. The oceans that covered the Earth's surface were partially vaporized. Mercury, the Moon, and Mars bear the scars of this massive bombardment. On Mars, the Hellas Planitia impact basin has been linked to the Great Lake bombardment by analysis of lunar samples. The basin measures around 2,200 kilometers, or 1,400 miles in diameter, and 9,500 meters, or 31,000 feet in depth. It is the largest impact structure on Mars visible from Earth. The basin appears as a bright area due to the high albedo of the dust constantly stirred up by the winds. The Hellas Planitia basin is surrounded by relief created by the impact. For over 1,000 kilometers, the terrain was raised. To the west, the edge of the basin is marked by a mountain range. In places, it reaches an altitude of 2,000 meters or 6,500 feet. To the east, the edge is marked by valleys, representing the beds of large rivers that have now dried up. Water was abundant in the impact basin. On the planet Mercury, the Caloris Basin is the most massive meteor crater known to date. It is located at one of the planet's 2 hot poles. Measuring around 1,550 kilometers, or 960 miles in diameter, it was formed by the fall of an asteroid with a diameter of around 150 kilometers, or 93 miles. The basin is surrounded by mountains, that rise to almost 2 kilometers or 1 mile in height. Its floor is filled with cooled lava, reminiscent of lunar pools. For some 1,000 kilometers or 620 miles, the material ejected by the impact forms rings surrounding the basin. The impact that formed the Caloris Basin is thought to have triggered volcanic activity on Mercury. The impact is also thought to have released heavy elements such as sodium and potassium from the planet's mantle. Being around 130 kilometers or 80 miles deep, elements could have been brought up from the mantle during readjustment movements. On the Moon, the Mer Orientale and the Mer des Pluies are basins that would also have been dug during the Great Lake Bombardment. The Mer Orientale is a lunar sea formed by the impact of a meteorite, which raised the mountains bordering the crater. It is one of the Moon's most impressive structures, with a diameter of around 900 kilometers, or 560 miles. 2 mountain ranges encircle the Mer Orientale: the Montes Rook, measuring 700 kilometers, or 430 miles in diameter, and the Montes Cordillera, measuring 900. The Sea of Rains is a sea found on the visible side of the Moon, formed when liquid lava filled a giant pre-existing impact crater, called the Basin of Rains. The latter is surrounded by 3 mountain rings, each composed of several mountain ranges. For some 800 kilometers or 500 miles, an area is covered by ejecta, forming a region of numerous reliefs. Asteroid impacts are common phenomena in the solar system. 160 million years ago, a collision between 2 large objects in the asteroid belt produced numerous fragments, known as the Baptistina family. The first body is located on the inner edge of the asteroid belt, just over 2 astronomical units from the Sun. Despite the fact that its growth is limited by the disruptive presence of Jupiter, it boasts a diameter of 170 kilometers or 100 miles, a very respectable size. It is one of the largest asteroids in the main belt. The second body involved in the collision is another asteroid, 60 kilometers or 37 miles in diameter. Its orbit is similar to that of the first asteroid. One day the two collide. The impact occurs at a speed of 3 kilometers per second, or 1.8 miles per second. It was so violent that the 2 asteroids were reduced to a dust of debris, which aggregated again to form a family of objects with similar orbital characteristics. This is the Baptistina family. This asteroid family comprises some 2,500 known members. Many years ago, we thought that some of them were responsible for remarkable cosmic collisions, such as the one that caused Tycho's crater on the Moon, or a direct collision with the Earth 66 million years ago. However, data from the Wide Field Infrared Survey Explorer in 2011 challenged this hypothesis, suggesting that the Baptistina family had in fact formed much more recently than previously thought, as recently as 80 million years ago. Consequently, the origin of the impactor that caused the extinction of the non-avian dinosaurs remains an unsolved mystery. Further study and exploration of the asteroid belt may one day unravel this mystery and help us understand the forces at work that triggered these impacts. Asteroids can undergo an effect that affects their rotation on themselves in the presence of radiation. When the object's face is illuminated by the radiation source, it receives energy. After half a revolution, This same face then goes into shadow, radiating outwards the energy it has previously received. The result is a very slight thrust exerted on the object, depending on its shape and surface condition. This is known as the Yarkovsky effect, named after the Russian engineer who discovered the phenomenon. Many individuals are then disrupted by Jupiter and the other planets. They find themselves injected into orbits that lead them to cross those of the Earth and Moon. 108 million years ago, an asteroid measuring 10 kilometers or 6 miles in diameter swung low over the Moon's western horizon and collided with it. The impact creates a huge impact crater called Tycho. This sends thin cracks across the Moon's southern hemisphere, extending to over 1,000 kilometers or 620 miles in all directions. The crater is located in the southern lunar mountains. It has well-defined contours, and its interior is characterized by a high albedo. The crater's diameter is 82 kilometers or 50 miles, and its rim rises to 4.7 kilometers or 3 miles above floor level. At that time, from Earth, it was the dinosaurs who witnessed this cosmic collision. Little do they know that they will be the next victims of these cosmic events. The Chicxulub crater is the most famous asteroid impact on Earth. It occurred around 66 million years ago in Mexico's Yucatan Peninsula and is associated with one of the world's largest mass extinctions. The impacting asteroid measures around 10 kilometers in diameter. On contact with the Earth, it formed a crater 180 kilometers, 112 miles in diameter. This suggests an explosion power several billion times that of the Hiroshima bomb. The crater basin is covered by about 1,000 meters, or 3,300 feet of limestone. It extends under the mainland and the Gulf of Mexico. Scientists are trying to explain what really happened during the impact that caused the demise of those who reigned supreme at the time, the dinosaurs. At the time, these gigantic, majestic animals had dominated the planet's animal ecosystem for 165 million years. They are the most imposing creatures the Earth has ever sheltered. Dinosaurs are very diverse and are found all over the planet. An asteroid in a region between the orbits of Mars and Jupiter is projected at several kilometers per second. It heads straight for the Earth until impact, forming a huge crater. The energy released was so intense that the rock of the Earth's crust liquefied. In less than a second, all the water within a 60-kilometer radius of the impact turns to steam. Animals in the vicinity are instantly killed. A few seconds after impact, the shock wave releases an unbearable heat that crosses the ocean. Everything in its path evaporates or melts. It would take just a few years for life to reappear in the impact crater, but over 30,000 years for a thriving ecosystem to develop. Scientific research has revealed the presence of burrows dug by shrimps and worms, as well as microfossils of plankton and algae. This suggests that the crater became habitable shortly after impact, even though the mass extinction was not yet over. Evidence of this impact was confirmed just before the 1980s. A thin black layer of clay just a few millimeters thick was revealed in some of the geological layers between the Cretaceous and Tertiary strata. This geological boundary contains abnormal levels of iridium. Although rare on Earth, iridium is found in abundance in certain meteorites. Scientists sometimes find minute quantities of iridium in terrestrial sedimentary rocks due to the fine, micrometeorite showers that are frequent on the planet. But analysis of this Cretaceous Tertiary layer reveals far more. This is why it has been suggested that the planet must have suffered the fall of a huge meteorite. At the time, the crater could not be found. In 1981, two geophysicists employed by the Mexican oil company Petróleos Mexicanos investigated the Yucatan and discovered this unusual geological structure. The fall of this meteorite marked the end of the Cretaceous period and was responsible for a climatic upheaval that led to the extinction of non-avian dinosaurs and a large proportion of the animal and plant species of the time, both on land and in the seas. Without this event, Earth's history would be totally different, and we certainly wouldn't be here to talk about it. The Vredefort Dome is the largest known impact crater on Earth. It is located in South Africa, in the territory of the Free State Province. In 2005, Vredefort Dome was inscribed on UNESCO's World Heritage List for its scientific and scenic interest. The town of Vredefort was built inside the impact crater. The asteroid's impact dates back 2 billion years. Until recently, it was the oldest known impact crater on Earth, until the discovery of Manliksok crater in Greenland, estimated to be 3 billion years old. The asteroid's diameter has been estimated at 15 kilometers or 9 miles. It left a crater with a diameter of around 300 kilometers or 186 miles. Vredefort is one of the few craters to feature multiple terrestrial rings, a phenomenon often destroyed by erosion and plate tectonics. The dome is only the central part of the astrobleme, which actually extends over 360 kilometers or 224 miles in length, from Johannesburg to Welcome in the Free State. South Africa's geological stability has ensured the crater's continued existence. It is one of the only craters to have been crossed by a river, the Vaal, for almost 280 million years. The asteroid's impact would have really damaged the planet, causing fires all over the world. The enormous quantity of dust thrown into the atmosphere would have altered the climate for years. Located in Ontario, Canada, the Sudbury Basin is a crater formed some 1.85 billion years ago. It is the second largest known impact crater on Earth, but also one of the oldest. It is located on the Canadian Shield in the city of Greater Sudbury. The Sudbury Basin is 62 kilometers or 39 miles long, 30 kilometers or 19 miles wide, and 15 kilometers or 9 miles deep. The diameter of the meteorite has been estimated at around 10 kilometers. Some of the rock fragments ejected on impact traveled more than 800 kilometers, or 500 miles, and were scattered over an area of 1.6 million square kilometers. Scientists even suggest that such an impact may have scattered debris around the world, but that it has since been eroded away. The impact that created the Manliksok crater is thought to have occurred around 3 billion years ago. It is the oldest known terrestrial meteorite crater, yet remains totally invisible today due to erosion. By analyzing the nature of the rocks, scientists were able to prove that it was an asteroid impact. The asteroid would have had a diameter of around 30 kilometers or 19 miles, and would have hollowed out a crater, originally 600 kilometers or 370 miles in diameter. At the time, only bacteria were beginning to populate the planet, but if such an object hit us today, it would exterminate all forms of life on Earth. Also known today as Meteor Crater, Barringer Crater is located in Arizona, USA, 60 kilometers or 37 miles east of Flagstaff. It is a well-preserved crater, formed by the impact of a small asteroid around 50,000 years ago. At the end of the Pleistocene, an object of peculiar composition hurtled towards the Earth. Made of iron and nickel, it is more likely to be a fragment of a planet core in the process of forming than a small body from the early solar system. As a result, it is much more resistant to the stresses imposed by the Earth's atmosphere than blocks of rock or ice. Once it reaches an altitude of around 14 kilometers or 9 miles, it eventually breaks up under the effect of increasingly dense layers of air. The meteorite splits into two parts, with a block of half its initial mass on one side and smaller fragments surrounding the initial impact over a diameter of 200 meters or 660 feet on the other. The main block, weighing 300,000 tons, hits the Earth at a phenomenal speed at 12 kilometers per second or 7 miles per second. The collision forms a crater over a kilometer in diameter. At the time, this area was grassy savanna occupied by mammoths and sloths. The impact releases energy equivalent to that of a thermonuclear explosion. All life is destroyed within a radius of several kilometers due to the blast and heat generated by the collision. The impact did not cause any noticeable change in the planet's climate. Meteor Crater is bowl-shaped, measuring almost 1,400 meters or 4,500 feet in diameter, and 190 meters or 620 feet deep. Today, it is a popular tourist attraction. Warburton Crater is located in Australia near the town of Ora Banda. Its diameter is around 5 kilometers or 3 miles. The asteroid's impact is thought to have taken place 100 million years ago during the Cretaceous, well before the impact that formed the famous Chicxulub crater. The Warburton Crater was discovered in a very flat landscape. Erosion has taken its toll, and there's no sign of a crater on the surface. The impacting asteroid must have been between 100 and 200 meters in size, or between 330 and 660 feet in diameter. The crater is buried under several kilometers of sediment. It is not a single impact crater, but two craters, 200 kilometers or 125 miles wide, forming a structure 400 kilometers or 250 miles in diameter. The two impacts may have occurred simultaneously due to the fragmentation of an asteroid. The Popogai crater is located in Siberia. It is the fourth largest known terrestrial impact crater, with a diameter of around 100 kilometers. It was formed by a meteorite impact 35.7 million years ago, during the Upper Eocene. It has been designated a geopark by UNESCO as a site with a specific geological heritage. Popogai is also the world's largest diamond mine. During the Cold War, it was kept secret for decades. Shock waves from the impact would have instantly transformed graphite into diamonds within a radius of 14 kilometers or 9 miles. This mine would contain the equivalent of 10,000 billion carats. Just over 200 million years ago, an asteroid hit the north shore of Quebec in Canada, forming the Manicouagan crater. It is one of the oldest and largest impact craters on the planet. Due to erosion caused by glaciers, it is not easily visible on the Earth's surface. Its concentric structure, around 100 kilometers or 62 miles in diameter, is explained by the shock waves transmitted during the impact. The meteorite responsible measured around 5 kilometers or 3 miles in diameter. Comet Shoemaker-Levy, sometimes abbreviated SL9, is famous in astronomy for being the first to offer direct observation of a collision between two solar system objects outside the Earth. It has been closely observed by astronomers from all over the world. Comet Shoemaker-Levy broke up as it approached the planet Jupiter, colliding with it in July 1994. This collision led to the discovery of new elements about Jupiter and highlighted its key role in reducing the amount of space debris in the solar system. This comet is unusual in that it has been orbiting Jupiter for some time, rather than orbiting the Sun, like all the other comets known at the time. By 1992, it had already passed very close to Jupiter, just over 40,000 kilometers or 25,000 miles from the cloud tops. The 1994 collision was by far the closest and resulted in the comet's fragmentation. Each fragment is designated by a letter, ranging from fragment A to fragment W. The 1994 encounter was eagerly awaited. Astronomers had prepared their terrestrial telescopes, and several space observatories were ready to observe the impact live. On July 16, 1994, at just over 8 p.m., Fragment A struck the southern hemisphere of Jupiter at a speed of around 60 kilometers per second, or 37 miles per second. A fireball then formed. A fireball was formed reaching a temperature of around 24,000 degrees Celsius, or 43,000 degrees Fahrenheit, before dropping rapidly to around 1,500 degrees Celsius, or 2,700 degrees Fahrenheit. After this initial impact, observers see a huge black spot. These were the effects of impact debris. Over the following week, 21 impacts were recorded, the largest of which was produced by Fragment G. It took place on July 18th at around 7:30 a.m., creating a giant dark spot over 12,000 kilometers or 7,500 miles wide. On July 22nd, the final fragment, Fragment W, struck Jupiter. Direct observation of this collision provided a wealth of information about Jupiter. The planet has since been regarded as a kind of cosmic vacuum cleaner within the solar system. Jupiter's strong gravitational influence attracts numerous small comets and asteroids. Its impact rate is estimated to be between 2,000 and 8,000 times greater than that of our planet. In other words, if it weren't for Jupiter, asteroid impacts on the other planets in the solar system would be far greater. Astronomers have even gone so far as to hypothesize that without Jupiter to intercept potential impacts, collisions leading to mass extinctions, such as the cosmic impact that caused the Chicxulub crater, would be much more frequent, and Earth would certainly not have been able to witness the development of complex life forms. The study of past impacts, their frequency, and the reason why they occur allows us to better understand geological history. Collisions play an essential role in the formation of new galaxies, for example, and help us to understand these complex structures and their gravitational interaction. The study of impacts enables us to retrace the history of bodies and better understand the processes of accretion and planetary differentiation. Gravitational interactions between bodies during collisions can help scientists map the distribution of matter in the universe. Far beyond understanding the universe itself, the study of past cosmic collisions enables us to predict future events. In a much more distant future, around 4 billion years from now, our own Milky Way galaxy is predicted to collide with its nearest neighbor, the Andromeda Galaxy. Scientists now determine that the two galaxies are heading towards each other at more than 100 kilometers per second. Even if the stars, because they are so far apart, pass each other without colliding head-on, the interstellar clouds will interact until they form a blaze of stars that exhaust almost all the available gas. This collision is considered a major encounter and will have a significant impact on the structure and evolution of both galaxies. Current research suggests that they will merge to form a new elliptical galaxy, devoid of interstellar gas. The latter will remain dominant in the local group. The sky as we observe it today is ephemeral, even if the changes in the course of a single human lifetime are infinitesimal. But in a few million years' time, the map will be completely different.